In this video, I will take an attempt in this live Kaggle competition where the problem is to segment the stomach and the intestines from patient images who are diagnosed with the cancer of the gastrointestinal tract. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So let's first understand the problem of the competition. So here is the overview page of Kaggle that I'm looking at, and what it says is that in 2019 an estimated 5 million people were diagnosed with the cancer of gastrointestinal tract worldwide. Of these patients, about half are eligible for radiation therapy, usually delivered over 10 to 15 minutes a day for 1 to 6 weeks. And radiation oncologists try to deliver high doses of radiation using X-ray beams pointed to tumors while avoiding the stomach and intestines. With newer technologies such as integrated magnetic resonance imaging and linear accelerator system, also known as MR-Linacs, oncologists are able to visualize the daily position of the tumor and intestines, which can vary day by day. In the scans, radiation oncologists must manually outline the position of the stomach and intestine in order to adjust the direction of the X-ray beams to increase the dose delivery to the tumor and avoid stomach and intestine. So this is the crucial point why this segmentation is so much important. So this is a time-consuming and labor-intensive process that can prolong treatments from 15 minutes a day to an hour a day, which can be difficult for patients to tolerate unless deep learning could help automate the segmentation process. A method to segment the stomach and intestine would make treatments much faster and would allow more patients to get more effective treatment. And that's the whole story of this competition, and this competition is being hosted by UW Madison Carbon Cancer Center, and they're a pioneer in MR-Linac based radiotherapy. So in this competition you will create a model to automatically segment the stomach and intestines on MRI scans. The MRI scans are from actual cancer patients who had 1 to 5 MRI scans on separate days during their radiation treatment. You will base your algorithm on a dataset of these scans to come up with creative deep learning solutions that will help cancer patients get better care. For example, this is an example image, and in this figure the tumor, pink thick line, is close to the stomach, the red thick line. So this is the stomach image, and this pink thick line is the tumor, and the doses should be directed here but should be avoided in this region. So high doses of radiation are directed to the tumor while avoiding stomach. The dose levels are represented by the rainbow of outlines, with higher doses represented by red and lower doses represented by green. So because this is the tumor at the very center, the high doses are given, and then as we go outside of the center, go away from the center, less and less degrees of doses are given, because now I'm moving closer to the stomach. So and that's the reason this green outline is where the minimum amount of doses are given, and this red should be completely avoided. So then cancer takes enough of a toll. If successful, you will enable radio-oncologists to safely deliver higher doses of radiation to tumor while avoiding the stomach and intestines. This will make cancer patients' daily treatment faster and allow them to get more effective treatment with less side effects and better long-term cancer control. All right, so that's a whole story and the problem of this competition. And of course, if you win, this is the prize amount they have indicated, and also you will get ranks in the competition. Actually, you can see the timeline here. April 14th it started, and July 14th is the final submission deadline. And now if I go to the data tab, this is my data set. It's comparatively low in size, only 2.47 GB. and in my train.csv I have all the IDs of the patients and the segmentation. So see one thing, that each of these ID is so first this is a case number, so 1 2 3 is a case number which represent a single patient. Then each patient is given this radiotherapy over several days, so each day is also this second part is a day number, and then finally this is a slice number. Each day multiple scans are taken, so each of these slice number is represent that. So because we are taking scans for large bowel, small bowel and stomach, each of these will be repeated 3 times. Each of this ID in the ID column will be repeated 3 times for large bowel, small bowel and stomach. Then again for the next one, which is 002, I have repeated 3 times large bowel, small bowel and stomach. And inside the train directory, all this is the overall structure. Under train I have the case number, this is a single patient. Then inside case number I have various days, day 20, day 22, 26, 32. And if you go inside the day, then my scans, and within the scans I have individual images. So these are all masked images, and that's why we are seeing them black. When I plot them with matplotlib in my Jupyter notebook, we will visualize actual images. So you can see that for this patient on day 20 I have so many almost like a 19 or 20, oh more than that actually, yeah, 114 more, so almost like 150 slices, 50 scans for this day itself. I have downloaded this data set in my local machine, so I'm starting the project in my VS Code, and as usual with all my other projects, let's create the files first. And I also need a Jupyter notebook file, of course, UW. I'm going to bring in all my libraries first. Also here for now I'm copying and pasting all the libraries in all the files. Later, after the project is done and after my coding is done, I will clean it up from individual files. All right, in my config, first I need to define a couple of basic stuff. Oh, I also need to import the OS. Let's do it here as well. Batch size, yeah, I'm actually going to define at 16. The box 10. These are some directories: Kaggle this train root directory and test root directory here, it's for Kaggle, and in my local machine only a slightly change in the directory structure. And now I have already imported that config in all the individual files. So let's quickly see my the train .csv file. That is our dataset has a train.csv file. Let's quickly see that in my Jupyter notebook. Run all and select Python 3912. Yes, so that's my train.csv. Segmentation, class, and ID are the three columns. Now print a quick basic plot for showing the large bowels, stomach, and small bowels. Fixed size will be, let's give it 28 and maybe 12. Train df original dot, sorry, class, because that is in the class. Values count, and I'm going to give normalized equal to so this will be a pie chart. Invar MALIZE white saying normalize is not defined. Oh yeah, so the method is value counts. The S is here. It's still saying, let's just run it. Normalize is not defined. Why is that? Oh, of course, mistake here. That's equal to. Yeah, so that's my pie chart. And now I also want to define a variable testdf reading these sample submission.csv, and that should return me an empty, yes, an empty data frame. Now, if len take the first 300 rows. The segmentation should be renamed to prediction. Debug false. Submission. Yes, so now it's this data frame has the first 300 rows from the train DF original, and that's what I'm showing here. And now I want to make some changes in the original train data frame, that is this one, and I want to create columns with case, day, and ID, and slice separately. So all these day 20 day, the day number will be a separate column name, and case number also will be a separate column name, and a slice. So for that I need the old famous glob module, import glob, and then if I just quickly first checking one running glob.glob, to that I need to pass my root directory with some asterisks, because remember, if we go back to our data directory, this is my train, we did need case, then the case number, scan, so I need 1 2 3 asterisks. That's what I'm giving here. Actually 1 2 3 4, because 1 second, I need to go inside this. Yeah, 1 2 3 4. After 4 subdirectory I go to the actual image. And if we print this, yes, that should give me the full path starting from the base path of this file, full path of the images. Yeah, this was just for checking that it's working, so clear the cell output. So now I'm going to create a function to create detailed DF from train DF. df case will be equal to df, then id. I'm going to use a lambda function here, apply lambda x. I need to split the current input, the current this whole string by these underscore, and then take the first element of the returned array, and then remove the case, which I can do by replacing this case string with an empty string. So my x will be split by the separator underscore, take the 0th element, replace case with empty. That should work. Do the same for let me quickly id day. Yep, so I need to do the same for day, so that would be id apply replace day. Similarly for slice, but here I do not, here I need 1, and here I need split 3, and because there is nothing to replace here. Okay, I'm having an extra something. I don't need the int here, so I can here. Now if subset equal to train or G, in that case my dir will be train with dir plus train, else dir will be equal to test root dir, and that is all. All right, now I need to make use of the glob to get my all images. Which will be glob with dot path dot join dir. Now I need to recursively get all the file names. So previously I used glob.glob, but instead of using this glob.glob twice, I'm going to use single time and then pass my this argument star twice, and then the file extension name which is star.png, and then I need to pass another argument called recursive equal to true. That should return me all the images, and x will be all images. 0 but r is r split. To that I will give 4 0 path partial list variable will be df.shape0. Partial list and os.path.join x. To that I need to I missed the dot here. So this x, actually if I print this, this will give me the train root directory. So yeah, this will be just this. And why I need this x is because in the data frame that I'm going to create now, that will have one column which will have the full path name of all the images, but I have to rebuild that because that's because, one second, in these lines here I have already split the original these id column values into separate case number, day number and slice, but then again I have to rebuild that, and that's why I have to start with this string here. And for rebuilding, join os.path.join x, and to that I have to join one by one all of them. So let's do that. Yes. Okay, so I have to take the values from this. Then to this I also need this time I need yes, values I. To that I need to add an underscore. That should do. And this will make sense if we just look at the data tree structure again. So I have this case 101. Within that again I have to add this case 101 underscore day and then the day number. So this case 101, this comes twice in these two subfolders. All right, now next string I have to add is scans. And finally the slice and the slice number. Slice, that would be underscore plus str. Values I. All right, now come out of this loop and df let's make it equal to path partial list. Now make path partial list equal to empty list again. Be path partial list dot append, and I want to append here. Okay, before that I think I missed out explaining one thing, that why I am running this loop again, because I already created this path partial list over here and rebuild my path with this running this loop, going through all the individual rows of the df. Now the reason that I have to create another loop here again is because what I am basically doing in this function is creating a data frame which will have a single column named path holding the full path of all the images in the data frame. But I cannot simply create them with the code something like let me show you. I cannot simply create them with the code something like this, that is this line, because if I do all images, and all images is of course defined, let me put this line here, because now I have my all images defined, and if I could have done this, but this will not work because all images is individual images. But remember, as we saw that this data frame, our original data frame, has those images repeated, because for each slice I have the segmentation, that is large bowel, small bowel, stomach, and so this first row is repeated 3 times. Similarly, second row is repeated 3 times. So to have those repetition and also have my path column which will hold the path of all the images, I have to create another temporary data frame and then merge the temporary data frame with the original data frame. And I actually tested the code running it like this, and then I will obviously get the length mismatch error, and the error that you will get if you just do this is something like this. value error, length of values 38496 does not match length of index, because this is the number of images in my train folder, and this is the total number of rows. So this will not match, and hence you will get a value error if you do something like this. So let's delete those paths. So here in the second loop here that I'm writing just now, that's where I'm actually trying to create a new data frame, and to add to the data frame this path partial list, which will hold my path of the images up to let me go back to the dataset, up to the slice string, So what I'm trying to do, let me put that in a comment. This is what I'm trying to do in this loop, that is now creating another temp df. For that, first I need the list of all images up to the string slice num. So I have to get that up to this string with this kind of code, str all images 4, then on that apply a r split, which will split by underscore, and then take the 4th and then take the 0th. Actually that's what I'm going to do, but let's take this whole code here from this cell, because this is just a simple independent method. Let's take this whole thing into my utils file, because that's how I want to arrange my codes in the project. So my notebook will only contain the actual execution, or actual wherever I am actually dealing with the data to show the final result, but all individual methods and utility function will be in these files, strength.py and utils.py. And after I brought all these code into my utils.py, I am getting debug is not defined. That's obvious, because I defined the debug in my Jupyter notebook right here. So for now, just put debug into the argument of this df preparation method, and pass it a default value of false. And now also obviously, to use any files, any methods defined in utils and train, I need to import all the methods from those two files into my Jupyter notebook, and that's what I'm doing. From utils import star, from train import star. All right. So where was I? Now I need to create this path partial list and hold my the string up to this slice. Yeah, that's what I was. So all I need to do is append all images. Yep, all images, apply r split, and split it by underscore number 4, and then take 0th value. Define the temp df pd.dataframe path partial list. Nope, it's an empty data frame. pmp underscore df, then define path partial. All images. And now my final df, the merge data frame, will be df.merge. I'm merging a temp df on the column path partial, and then after the merge I need to drop this unnecessary column because now the use of these has already been taken. Now I no more need that. Columns path partial. Similarly to this merge data frame, I need the width column EH, which will be df path let's take integer value of x. Integer value would be, yep, I'm right, -4 dot r split split. To that I pass 4. It will be 1. Similarly, height will be four, 4, 2. Okay. Finally, delete that x variable. Path partial, not path, path partial list, and also temp df. These are all large, except the x, both of these kind of large variable, so it's better to delete them. Finally, return df. So basically our problem is solved because we know that this path is repeated in the dataset. But now these merging between the temp df and original df is based on this path partial, which is this value, that is up to slice 0088, and this is unique, this is not repeated, and hence these two data frame are merged on these unique column value, which is path partial, and so that pretty much solves the problem. Now this merging is based on these unique values, and this path is repeated. I mean, in the final merge data frame as well, obviously this path, because that's the number of images, that will be repeated, but no problem because we have merged them based on a column value which is not repeated, which is unique, which is this. And now if I come back and in my notebook and run that df preparation method, let's just print the first 10 heads. Yeah, so that's my new rearranged data frame. I have the ID as original, then I have the class, then all the case number, day number, slice number. This is the full path and width and height. By the way, I forgot to mention the way that I got this width and height from the images is like this. Here in each of the image, this gives me the width and height of image, and this gives me the width and height, that's actually pixel size. So that's how the naming convention is in this competition. All right, now I just want to quickly, I cannot see the full path name here, so just want to quickly print the first 4 path name to see that they are actually right one. Yes, indeed. We can see that the first, each image is being repeated 3 times in this data frame for small bowel, large bowel, and stomach, and then the 4th is the new image. All right. So that was my train df after rearrangement, and I want to do that same for my test df. List index out of range. Let me fix it. I think this is coming because of this argument that we have, debug equal to false. So and the condition is if subset equal to train or debug, then only my directory will be properly set to the train root directory plus train. This is where all the images are there. So when I'm running here without passing any debug, my directory will be set to this test root directory, but there is no images in that directory, and that's why I'm getting list index out of range, because there is no list of images at all. So just pass debug equal to true and then run again. Yep, now it's working fine. So now my test data frame as well got rearranged with case day slice column and the path. Okay, just quickly check test df path 0. Yeah, it's printing the full image path as expected. Okay, now I also need to do this thing. Rearranged my train df, and why I need that is because as we discussed that the original train.csv, for each id I have 3 duplicated rows, because we have 3 associated rows representing the segmentation for 3 classes: large bowel, small bowel, and stomach. And now what I want to create is extra 3 columns with the same segmentation names and assign corresponding values. So what I will do, create a method and extract those 3 column values. So let's go to my utils file. Now let me quickly okay. Subset will be equal to train. pd.data frame. Yep, yeah. No, actually id will be df id. I'm going to extract, I'm going to use slice notation to take every 4th value. That is, I'm going to skip 3 values because 3 are repeated. So colon, start and stop, and then my step, that is a 3rd argument to this, will be 3. Yeah, yeah. If subset equal to train by structured vowel equal to will be df segmentation. Take the every 4th values .values, and similarly for I have to do the same for small bowel and stomach. Okay, now df And also similarly, I have to take the every fourth value for the other columns. That is, I have, if I go back, I have all these column: path, width, height, then I have case, day, slice. So I have to do this for all the other column. Restructured. Let's do it for path. df path. I take 3 values. Do it for all the other ones, which are yep. Yeah. Now I want to do a reset index. Df structure dot reset index drop true. And also I want to do fill NA with empty string. Structure dot df restructured fill NA. Okay, anyway, df subset. And lastly, just add a new column called count for those segmentation, which will be np.sum restructured. Integer location. Now take one, two, 4. So I'm summing up starting from 1, ending at 3. Yep, only when that's not equal to empty string along axis 1. That is along the column axis. Why I'm getting values? I have a syntax error here. np.sum I have these extra braces here. All right, now return this restructured df. Now come back to my train df restructured. I'm creating a new variable, and now in my Jupyter notebook just run that method, and that's my rearranged data frame. So now I have large bowel, small bowel, and stomach as 3 separate columns. So that's kind of my final data frame that I'm going to use because it has been completely rearranged. But now when I was going through the competition discussion forum, there is this discussion here about some of the data being corrupt, possibly. For example, here this discussion talks about, it seems, a mask for case 7 day 0 and case 81 day 30 are incorrect as they don't line up with the anatomy. So you might want to leave them out of your training. So if you look at the mask, obviously it doesn't really match up. So so was the case for another for case 138 as well, that I found out when going through all the discussion forum. So I'm going to keep those three cases. I'm going to take out those three cases. So I'm going to use this code to clean up my train df rearrange to so when only take those numbers, those rows where these case is not 7 and day is not 0, case is not 81, day is not 30, and case is not 138, day is not 00. All right, run this cell, and with that now I am ready to let's quickly run gc.collect, because of course Python is garbage collected language, so it will do garbage collection as and when a function returns. So I'm just running it for extra, because I'm running this entire thing in my local machine, and sometimes some variable leaves, and that makes my notebook pretty slow. So anyway, now I'm going to do few more util function which are pretty famous for doing any computer vision project, that is segmentation project, which is RLE encode, RLE decode, that is run length encoding and run length decoding. So before doing that, quickly go through what is run length encoding is. So I found out these great blog q-viper.github.io about run length encoding, and what this blog talks about as that this is a lossless compression algorithm, and it is very simple to practice on. The concept of RLE compression is that check for the consecutive runs of the current pixel value. This algorithm works based on binary images. So they are giving an example here. Let's go through this example, then it will be absolutely clear, because you are going to use these run length encoding and decoding in almost all segmentation projects in computer vision, because most of the projects to save the data space and make the calculation efficient will have the numbers given which are in this format, that is they will be encoded by this run length encoding algorithm. So we have to decode it and also encode it from time to time in any project. So let's take an example image. So this is an example image 10111. These are all pixel values, and of course this looks like a grayscale image because all values are between 1 and 0. Have 16 pixel and it is binary. Now using RLE we do something like below. At the beginning, current pointer is first value is 1. Now compressed image 1 1, which means that 1 has repeated one time consecutively. So this will be the encoded value of the first pixel. Next value is 0. Again it is repeated one time, hence compressed image is 1101, because this 0 has repeated one time, so I am putting it as 01, which means 1 is repeated one times and 0 is repeated one times. Next value is 1, that is this one. Now 1 is repeated 3 times, that is 1 2 3, hence compressed image now becomes 1101 and 13, because this one is repeating 3 times. Let me zoom it a little bit. Okay, similarly next compressed image is because this 0 is being repeated 3 times, so I will add 03 to my compressed image. Again the next one is repeating 2 times, so after 03 I will add 12 because the 1 is repeating 2 times. Similarly if I continue to do this, the final will look like this. So final RLE becomes this, that this was my original image. If I take this original image pixel values through an RLE function, the encoded value, the encoded format result will be this. So what it means is that ultimately our image had 16 values. Now it is compressed under only 8 values. And this algorithm is what I'm going to now code it up. So, and for this code, I'm referring a pretty popular repository in GitHub, and also that's used in Kaggle quite a few times. I'll give the reference link in my notebook, that the description, the link of which will be shared in the description of this video, so you can check the original. Because I'm using that particular, there's so many implementation of RLE encode. Of course, most implementation uses same algorithm that we just discussed, but this particular implementation has been pretty popular in Kaggle. Many people are using it because that's a very intelligent way to implement RLE encoding. The link is, let me put the link here. Yeah, this is the link. You can just go to this link to check it out, the original code. So that will take, RLE encode function will take a masked image and pixel. First I need to flatten the masked image. And now I need to avoid some issues with 1 at the start or the end, because at the corners of the original image, by setting those corners pixels to 0 explicitly, we avoid some issues, and we do not expect these to be the corners to be non-zero for an accurate mask. So adding these 0 value to the corner pixel should not harm the overall score. So what I'm going to do, pixel equal to np.concatenate, and I have to concatenate a 0 at the beginning, then goes my flattened pixel, and also 0 at the end. All right, now my runs, that is my run length encoding. So first, here in this line, I want to capture the indices wherever 0 changes to 1 or 1 changes to 0. Let me put that in a comment. Runs include indices to wherever 0 changes to 1 or 1 changes to 0. Now, this is the original code from where I took this, that is this link here. They implemented it in a very intelligent way, that is reversing the original list and then comparing them with np.where. So the code is np.where pixel. First I am taking 1 and then not equal to reverse the list, and to reverse the list you just have to take the slice, but you do the jump with -1, that is it will move by jumping 1 step from the end. And then here I need to add a 1. So the purpose of adding 1 here is to make sure that the indices point to the very first 1 or 0 of the 1s or 0s from the original pixel. This is needed because np.where gets the indices of elements before changing, and then I have to do that will be starting from 1, and the jump, that is the step is 2, and ending at the end. That will be updated with -= with runs 2. So basically what these runs 1 slice 2 will do is this. Let me put that in a comment. runs 1 to 2, that start, stop, step. Thus 2 here is the step. Similarly, for the other one, that is run slice 2, that also I'm putting that in a comment. That includes the indices for the changing from 0 to 1. That's why this jump. So these runs 1 slice 2, that is on the left hand side, this includes the indices of the changing from 1 to 0. And for the right side, this run slice 2 includes the indices for the changing from 0 to 1. So you will get a clear picture of these if you take a simple image, binary image of 1 0, and continue printing each line here and also each part of this line. And in that way, if you print each side of these expressions individually on an example pixel array, then it will become clear. Otherwise, just looking at the code, it's slightly tricky to understand. So anyway, this RLE encoding is already done in here, and I'm just now returning the final result, including a string, empty string between the elements. So join str, and what I have to do is put x for x in runs. That's all. And now to test that same function that I wrote here, I created a new Jupyter notebook and pasted the same function over here. And then I'm defining a test masked image to be this array. It's a two-dimensional array, np.as array, and then I'm running this RLE encode test mask. Okay, so another thing I just remember while doing this is an image, a binary image, and it is represented by this two-dimensional array, and all are 0 1 because it's a binary image, it's a grayscale image, and each represent a pixel value. Now, because this is a two-dimensional array, when we did a concatenation over here and added these 0 and 0 to cover the corners, these also need to be added as an array like this. So the first 0 should be converted to a single element array, and the next 0 as well. And let's now run this entire thing. Okay, I got an error, and the error says that can only concatenate tuple to tuple, and the error is coming from this line np.where. Okay, I got it. I think it's a way that np.where works. So if you look at the official documentation of np.where, it says that return elements chosen from x or y depending on condition, and the condition is the first argument. So check out their return value. It returns an array with elements from x where condition is true and elements from y elsewhere. So so the return value of np.where will be a list or an array like this. Okay, got it. So I have to take because I am only interested in wherever zeros change to 1 or ones change to 0. So I need to take that particular position. So I need to take the 0th element. And now if I run all again, yes, now it ran correctly. So this entire image got represented by this string. That's a run length encoded version of this entire long list. And similarly, I have to have a method for RLE decoding, but for the decoding part I will do the explanation maybe later in a separate video. Otherwise this video will become too long. Anyway, there's still many more things to explain about this project. So I'm just quickly writing the decoding code. Mask. So obviously this will take the mask RLE as the input and then decode it. So that would be mask RLE dot split. Starts and length equal to as array. From S, I will take, sorry, this will become ENS, starting from 0 to all, then one to all, and then all jump to. Shape 1. Flow 32. Now, what I'm missing, the all right, so that was my RLE decode, and I also need three metrics, three methods to calculate the metrics of performance of the segmentation. So those are very common: dice coefficient, IOU coefficient, dice loss, and those are three. And I also need a quick function called BCE dice loss. So let's define them quickly. These are very common function, and the implementation is also super simple, so nothing complex going on here. Dice coef will take y through pattern y true. Actually, I have a separate video discussing dice coefficient, so you can just check for that in my channel. Intersection is y true flattened multiplied by y Red flatten. And my union will be k dots sum to flatten. Then these are vectors, so I have to separately sum them. And the return value will be just intersection by union, of course, bringing in the smoothing factor. Of course, and here I'm calculating the dice coefficient, so I have to multiply by 2 at the top. So to make it float by bringing in the dot, multiplied by intersection plus smooth, divided by union plus smooth. Yes, that makes sense. And then I have to do IOU coefficient, intersection over union. It's almost similar to dice coefficient. So I need to first calculate intersection equal to k dot sum. Also I need to do k dot absolute widespread, and then I need to do this along the axis of 1, 2, and 3. And union will be k dot sum the axis will be 1, 2, 3. Plus k dot sum y spread along the axis of 1, 2, 3. From that I need to deduct intersection, otherwise it will be double counted. And now the IOU is just k dot intersection plus union sorry, that's not union. Intersection plus smooth, and that will be divided by union plus smooth. Along the axis of 0. And again, these 1, 2, 3 number that is passed to k dot sum, what do they signify? They means that the sum runs through the second to fourth axis of the tensor. And here these 1, 2, 3 are the axis. The smallest number shows the outer dimension, and the biggest number shows the inner dimension or the inner axis. And then the next thing, I also need dice loss function. So y true, y pred, smooth, then y true flattened equal to, and y pred flatten equal to y pred flatten, then intersection equal to k dot sum y true flattened into, sorry, it would not be k dot sum, it's intersection, so I need to multiply them. Y true flattened multiplied by y predict flattened. Why does it gives flatten, E-N-E-D? Okay, that should be a D here. Still I'm getting, yep. And then the score will just be 2 multiplied by k dot sum. I have to it would be 2 into intersection plus smooth by union. So my intersection is k dot sum intersection plus the smooth factor. And once again, this smooth is added again and again to all the function, and that is to avoid division by 0. And here I have to divide by the union. So k dot sum sum across y through flattened, and I also need to do k dot sum y pred flattened. 2 days I have to add smooth, and the loss will be return 1 dot minus the score. That's my dice loss. Okay, the last function I need is BCE dice loss, that is binary cross entropy dice loss. BCE dice loss, it will take again y true and y pred. And for the definition, I just kept a image for the definition. So this is the BCE dice loss. This loss combines dice loss with the standard binary cross entropy loss, that is generally the default for segmentation models. Combining the two methods allows for some diversity in the loss while benefiting from the stability of BCE. The equation for multi-class BCE by itself will be familiar to anyone who has studied logistic regression. Of course, you can recognize this expression here. It's with the logistic regression. Anyway, coming back to our util function, I need to define. So this will be, I have already imported binary cross entropy. Let's just check again. Where is my 1 second, I thought I have imported it. Yes, so keras.losses import binary cross entropy. That's what I'm going to use here. Return binary cross entropy, and I have to cast these with tf.cast y true and tf.float32, and then the next one will be tf.predict. Similarly, I will multiply the dice loss, which is 0.5 dice loss. Again, I need to cast it here with tf.cast y here it will be y pred. No, actually it is going to be y true, of course, sorry, y true float 32, and then the next one will be y pred. Yes. All right, I think that looks good. And now I have to build the data generator method Before that, quickly check these couple of points about the data set here. So this is the most important points before dealing with the data, that note that the image file names include 4 numbers. For example, 276 underscore 276 underscore 1.63 underscore 1.63.png. So this is the general format of each of the image, and these 4 numbers are actually slice height and slice width. That is, the first two, 276 and 276, are the slice height and slice width, and the next two, that is 1.63 and 1.63, are height width of pixel spacing, and they are in floating point in mm. So the first two defines the resolution of the slide, and the last two record the physical size of each pixel. And physical pixel thickness in superior inferior direction is 3 mm. And and if we look at the train.csv, I have 3 classes: id, class, and segmentation. The last segmentation is actually the run length encoded pixel, and they also says that in here, that is a columns id, which is a unique identifier for object. Class is the predicted class for the object, and encoded pixel is RLE encoded pixels for the identified object. And what do I mean by RLE encoded? So if we go down these train.csv, we can see this. For example, the stomach here, and I am looking at the third column, that is a segmentation column. These kind of numbers will be given. So most of the cells here are blank. That means that particular segmentation of within these 3 were not found, and that's why they are blank. And all the cells that has this number, that means this is the RLE encoded position of the stomach here. Or if I have similar number for small bowels, then that means that they found a small bowel with RLE encoded numbers. So yeah, so that's the data structure. Let's go back to our cell, and I have to do a new file here, and let's bring all the imports. First, I'm creating a method only to load the grayscaled image. I'm going to choose imread any depth. So when this cv2.imread any depth is set, that returns a 16-bit or 32-bit image when the input has a corresponding depth. Otherwise, converts it to 8-bit. Size of what? Defining the size. Resize. (32 by dividing by 255 to normalize. I also need to do expand dems, give it img, and around the axis of I want to keep it inferred -1. All right, that is done there. Now my dataset generator class. Data, and that would have tf.keras.utils.sequence actually. UNC. This batch size is coming from the config file. Let's just delete them. Shuffle. Self.subset. I also need to have indexes self dot indexes. I'm just defining it here to be the length of the mp.a range len of df. On epoch end. And now a quick note on these, because data generator class here is inheriting from tf.keras.utils.sequence, and when you do that, you need to note a couple of points. That is, every sequence must implement the get item and the len method, and if you want to modify your data set between epochs, you may implement on epoch end. That is this method. And the method get item should return a complete batch, and this method on epoch end is called at the end of each epoch and is usually used to shuffle the sample indexes. And overall, these sequence, that is this utils.sequence class, are a safer way to do multiprocessing. This structure guarantees that the network will only train once on each sample per epoch, which is not the case with generator. Alright, so now following that, I need to define the len. It is very simple method which will return me just the integer value of np.floor. That is, I need to length of the data frame divided by batch size. Divided by self.batch size. I'm also going to define on epoch end. Then I'm going to shuffle with from the random distribution. And what I'm going to shuffle is the indexes. All right. And the next get item method will be slightly longer. First, I'm just going to declare an empty array with np.empty. I need to pass the size of that. So my first dimension of this new empty array will be self.batch size. Then (128 by 128 by 3). Similarly, I need to create one y. Size remains the same. Index plus 1 multiplied by self.batch size. So here I'm just taking a single window of indexes, starting at index into self.batch size, then a colon, and my ending index is index plus 1 into self.batch size. And index is coming from the argument. And now the actual loop for getting the images based on the indexes. And I need to return mask and image. So let's just start this for I image path in enumerate self.df. I have a column name called path. From that, I take the row of, that is integer location, iloc of indexes. Yes. And also another point to note that in this competition, the channel order, this is my channel order, that is RGB, they conform to the sequence large bowel, small bowel, and stomach in terms of the channel sequences. And how did I get that? Because just checking the train.csv file in the original competition dataset, you will see that they are mentioned like this. That is, first is large bowel, then small bowel, then stomach. And also I went through some discussion forum in the competition to know to confirm this fact. Okay, now go back to my this thing, and now my next loop, that I have to loop through the 3 segmentation classes. For kj in enumerate, that will be a list of large then small bowel then stomach. Okay, now here J will take each value from these above list, and k obviously is a counter. So now I need to get the RLE, that is a run length encoding values from the train, from my train.csv file. And as you remember again that in the train.csv file, these large, small, and stomach, these three segmentation classes are actually given as run length encoded number. What I mean by that is this kind of thing, that is in the segmentation where we don't have a NaN value, those are given like this: 28094, then a single number 3, 28358, then a single number 7. And the significance or the meaning of them is that say 28094, 2853, 358, all these are the start points of the pixel within the matrix. Then because these are run length encoded number, that is, the first will tell me about the pixel value and then how many runs that pixel has. So the next single scalar number, these 3799 etc., actually mean how long to stretch that start point, meaning the total length of the run, total run length. And hence we can compute the end point of each of these segments as the sum of the start point and the end point. That's how these run length encoding goes. Of course, we have discussed these things earlier as well in this video, but I just mentioned it again. That's how my the segmentation values are given. And now in this loop, I need to get those segmentation values. So what I'll do is RLES equal to self.dfj, and then log indexes, then I again. And if you are wondering that how this is getting my RLES, that's because this J value here is actually these values. And we already know that we have created separate columns while we were rearranging the data frame. The original data frame had these three values as in vertical row names, but we have created separate columns for each of these values. So now in our rearranged data frame, we have three columns named like large bowel, small bowel, and stomach, and those column has these RLE encoded values. So if I just extract the values from this column, which is what I'm doing here, dfj, then I will get those RLE encoded values from it. And now the mask will be RLE decode. We have already created this method to decode our RLES. That will take RLES, and shape will be our H, W, and 1, because these are grayscale. And a mask, I need to do resize here, CV2 resize mask, and 128 by 128. Lastly, Y, I need to just get the proper slicing notation here. I for the first dimension, then all for the second dimension, all for the third dimension, and K. K is our counter here. So that will be equal to my mask. All right, now I can come out of these loops, and if subset equal to train, then return X and Y, else I need to return only X. Just keeping this method commented out for now. Later I will uncomment it. And here when I'm enumerating here, this I actually is the counter, and it values will be the total length of this part of the data frame, and that's 16 because my batch size is 16. So because here in this loop it will return me batch by batch data to be fed into the model. So this enumeration over these indexes is actually enumerating over a length of 16 number of images, and that's a counter for I. That's my width and height from the 16 number of batch size, 16 number of images, and these actually selects a row number of indexes I with this iloc integer location. So all right, now my image will be, I need to actually uncomment this because I'm going to use this grayscale image method now to load my image. So image will be self.grayscale image. To that I have to pass image path because that's what it takes. And now I need to set my xi equal to this image. So this will pretty much broadcast to shape of 128 1 by 128 by 3. And if you print image dot shape after these grayscale image, you will get a shape of 128 by 128 by 3 like this. So I actually printed it out and I was getting 128 by 128 by 1. That's what you will get because these are grayscale image. Yeah, and that's why I need this line, because now I need to broadcast these lower smaller shape into a higher shape. That is the channel number I'm talking about. All right, now before going further into running my next loop, I just want to go through this little quick note, which is about the relationship between the mask and channel number in the images in this dataset. That for each ID we are going to create an image of shape, image height, image width, and 3, where 3 is a number of channels, and these 3 layers for each class. That is, the first layer is large bubble, and the second layer is small bubble, and the third layer is the stomach. So that's how these masks are defined. That is, this large bubble is one channel, small bubble is another channel, stomach is another channel, and then when I want to plot all the 3 channels, like in this here, that will plot all the 3 masks. And after that I want to create a quick bar plot, and for that I need to define a method for plotting the bars. And what kind of bar plot I want to create, that is, if I go back to my notebook, we have seen after the rearrangement of the trained data frame, this is my rearranged trained data frame. That is, I have my 0 is the index number for the first column, and then from 1 2 3, these 3 columns I have large bubble, small bubble, and stomach, and this is the contents or values of these 3 columns, which are RLE encoded segmentation pixelated data. and I want to create a bar plot of the percentage training images with mask. That is, how many of total images have a large bowel segmented, how many of the total images have small bowel, and the percentage of stomach. So let's go to my utils file. I need 3 plots for the three columns, and the values will be the mean of those 3 column values. So I have to create np.mean, multiply that by 100, and to this I will pass df.integer location that would contain my all the rows, and that's my first dimension. And for the second dimension I will give, that is a column dimension, I will start with 1 and end at 3. That means I have to give it 4 along the axis of 0. And then regular stop plt dot plt dot title, then plt dot y label would be percentage of train images with mask. Yes, percentage of train images with mask. And also I want to give plt.x, actually give it next line, plt.x label would be class types. This is just the 3 classes. Now I have to run a loop for between bar and labels for rector get x width, get width will be divided by 3, and bottom is equal to 12. Little change here, it would be where I cannot take the entire column, so I have to make a condition where it's not equal to an empty cell. And then I come back to my Jupyter notebook and run this cell, passing a train df rearranged, and I get bar plot like this. So this is a total percentage of these three classes of segmentation data that I have. Now I need a method to plot some of the images along with the color patches. So I need a method to which will take the data frame and some colors and labels and return me a plot of images and the mask side by side. So let's build that method. Mask with patches. So here, first I need to generate a random set of indexes that will contain some values for the large vowels, and similarly I also need to include all the indexes which will contain some values for small vowels and the stomach. That is, I cannot have empty indexes here, because in that case a plot, because I am building this function to build the plots of the mask, so I definitely need some images where some of the mask has been identified for the three segmentation classes. So mask indexes will equal to list. Now I need to access the data frame and then df. And the first one is large vowel. That should be not equal to empty. Take a sample of a batch size number of images and get their index. I need to do this for my small vowel as well, and similarly for the stomach. Now if I print these masks, it will be something like this. Something like this, a whole list of indexes. Actually change this name to something else, because these are like my list of indices of mask randoms, so let's name it like this. Size. Create a grid spec. Num rows and in columns will be 2. Color equal to colors I. Label, let's first complete this statement, then I'll come to label. For I in range and label equal to and now I need to create some color for the three segmentation that I have. CMap 1. So here I'm going to use this module of matplotlib called colors.listedColorMap class. So these listed color map class is used to create color map objects from a list of colors. The class belongs to the matplotlib.colors module. This module is used for converting color or numbers arguments to RGBA or RGB, and for mapping numbers to colors or color specification conversion in a one-dimensional array of colors, also known as color map. And this can be useful for directly indexing into color map, and it can also be used to create special color maps for normal mapping. And the code is just simple as this: mpl.colors.listed color map. To that I pass my colors list 0. So in the next line I'm going to do colors 1 and name it as 2. Similarly 2 and 3. Now my loop starts over the number of rows. I always make a mistake. Oops, I think I need another variable that I forgot to declare and define it here. Yes, I need batches from the data generator. Batches from data gen, which will receive the output of my data generator method. And again I need to use the df with a condition. df.index.isIn list indices mask random shuffle true. Why it's saying data generator is not defined? Okay, I just need to import those two files, just like okay, from data gen import star let's go to mine. All right, now it's still saying data generator. Let me see. Yeah, I just have to restart the VS Code. It's crazy. It was not recognizing these data generator class. Anyway, now it's all fine. So my data generator should give me batches from data gen, and that is what I'm going to take here. So here for each ID we are going to create an image of shape, image height, image width, and 3, where 3 is a number of channel, and the 3 actually referring to the 3 segmentation in this data set. That is, let me put that in a comment so that it becomes clear. Yep, the first layer is large bubble, then small bubble, and stomach. So I'm going to take a sample image, images 0, everything from the second dimension, everything from the third dimension, and 0 index from the last dimension. And I need to create 3 masks for these 3 layers. It will be 0. That's only mask. Oh. The subplot by the way, these GS we have defined here. That's a gridspec.gridspec of matplotlib module. This specifies the geometry of the grid that a subplot will be placed. The number of rows and the number of columns of the grid need to be set, which we have set here. And it optionally also takes the subplot layout parameters, so which are left, right, etc. I have not used that here. So grid spec becomes really indispensable when you want to you want to change the different size of the grid. But here in this case is rather simplified implementation of that, so I do not have to go crazy into that. So just proceed normally. Okay, now I have my x0, x1 defined. Now if I equal to 0, that's when I have to set the title x0 dot, sorry, set title font size 15, widths x1 is my mask. Endless. The box pattern, the box to anchor. I don't see that. The box, the box to anchor. Face color, I need to give, let me bring it. Oh no, sorry, this face color not here, sorry. I need to provide the LOC parameter and also border AX spread, yes. Title equal to mask labels. What else I need to give? Title font size. Font size, let's give it 14. Edge color black. Face color, no, I need to change the face color to something else. All right, now I need to define my define various ax.inshow variables. So let's L0 would be ax1 dot this will not be sample image. Now here I'm going to use the masked where module of NumPy. It is a module or method to mask some areas of the photo of an image. So let's quickly, before implementing that, quickly check out one particular note about this, because in that case it will be clear. So I'm going back to an empty Jupyter notebook. So the thing that you have to keep in mind in this project is that mask 1 represent all the area that is large bubble, mask 2 represent all the area that is small bubble, and mask 3 represent all the area that is stomach bubble. Now, sorry, this is not stomach bubble, this is only stomach. Now, when the way that mask square will be applied is that it will mask some areas of an array based on a condition. So when the condition that I will pass to mask square, when that returns true, those areas of the array will be masked. And so let's do that then. Where was I? Yes, np.ma, and that will be masked where as masked where, sorry, where. Now here I have to pass the condition, and my condition is mask 1 equal to false, and the array is mask 1. So whenever this condition is true, that is all the areas in the array where my mask 1, that is a small bubble, is not activated or not recognized, that is it's false, those areas will be masked by this line. And cmap 1, oh, I have already defined that. See, and put alpha equal to 1. This will control the transparency. And now I have to do for my L2, this will be my mask 2 and mask 2, and this will be cmap 2, and then here L3, oh sorry, the previous line, this would be okay, no, this would be x1 only, and yeah, np.mask3 is equal to false in my mask 3. Yes. All right, and lastly I also need to define this aax.set axis of. For AX in AX0 and AX1. Colors will be equal to im.cmap im.norm1 for im in L1, L2 and L3. All right, now that this method is complete, I just need to execute this method in my notebook. So this is what I do. I just executed this method plot mask with color patches and passing that my train df rearranged and also these colors and labels. And if we have forgotten what this train df rearranged is, this is this data frame. So I have on the ID large bowel, small bowel and stomach and the other values. And the most important thing in this case while plotting is these RLE encoded segmentation pixel values. So let's just run this cell. All right, I got the image and mask, but if you can figure it out that this is not the correct one, because these masks should be printed in different colors. Large, small bubble should be blue, green and red, RGB, but it's printing all red. And actually I found out the problem here. There was a bug in my code in this method. I come to my utils file and I have a method here, or yes, this one, df rearrange for segmentation classes. So this is the method we used for rearranging the segmentation classes, taking them from the vertical row values to individual column values. And here I made a mistake earlier, which is when in these lines. So I think you can already note that when I was taking the segmentation values from to build the data frame, I was slicing it wrong. So I was jumping by 3, but I was always starting from the starting index position. That should not be the case. It should be 1 here and 2 here, because the first comes large bowel, then small bowel and then stomach. And so that's why my starting position should be shifting by 1. So the first one starts from the very initial value index position, the very starting index position. The second one from the second position and the third one from the third position. So now it should be working fine. And after making those correction, I ran it again and now I'm getting just the perfect mask coloring here. So these for example, in this image, this is my stomach and this is the large bowel masking. All right, now next step is to do a k-fold cross validation. And for my k-fold cross validation, this is a case of medical images and also with a high level of class imbalance. Hence I'll be using the most common one in these cases is stratified group k-fold cross validation. Because in this kind of situation when you have large imbalance in data, because here very few cases has the tumors identified and most cases the mask is actually blank, that is there is no tumor. In this kind of unbalanced cases, these unbalancing behavior of the data set will be handled or taken care of by stratification. Hence I'll be using that. I have a separate video actually discussing all the different k-fold techniques and methods which are available and in which cases we should be using which one. So if you are interested, you should check that video out. And there I have also discussed why for medical diagnosis or medical image classification cases, most of the time this stratified group k-fold is mostly used. And Another important factor is that in a stratified group k-fold, the single patient, there is a group constraint concept, and fundamentally that means that that a single subject or a single patient must not appear in different folds. So we have to make sure about that, and we will see about that in a second. Let's start the actual coding. I have already imported this stratified group k-fold at the very top from sklearn. So I can just strati group k-fold here. Number of splits is just the number of fold, which is a hyperparameter. Random stat equal to 42. Now I have to enumerate through the through my data set. Before that, for fold, yep, x will be equal to my train df rearranged, y equal to will be the counts, and here is the most important thing, the group constraint concepts, GROUPS. So because single patient in this dataset is identified by the case number or the case column in this data frame, so I will be choosing case as my group. Oh, sorry. NDF rearranged case. And when I mention these stratified group k-fold algorithm of sklearn internally will make sure that this subject is not repeated in two folds in a same iteration. That will be one here, and I think I'm making some mistake in the formatting. Let's just copy and paste it into a Python file so that it gets automatically. Okay, this is not happening. Okay, let's just go with it and I'll check. All right, yep. Unsigned integer uint 8. Rearranged. Oh, sorry. This will be train df rearranged, and then oh yeah, I was doing right because it's a condition that I have to put in. Fold cannot be equal to fold selected. Similarly, valid IDs will be train df rearrange fold selected index. Okay. X train train and if we arranged it will be actually I want index dot is in train IDs. Similarly, my X valid will be index is in train valid IDs. Arrange that group and after I ran this cell, I got these different folds, and these are the number of images taken. So we remember that in the config file we defined this fold to be 5. That's why I'm getting this 1 2 3 4 5. Right now I am going to do another group by here. Column not found ID. Okay, let me check. All right, that was a small typo mistake. Okay, so now I have this data frame. We can see that the folds, we have 5 folds, and these are the values. Now the next thing I'm going to check that my submission format is working properly. So a quick code PERUNT string.guess xtrain.guess.unique. Take our first 5 values. Similarly, x valid print x print.hpe and also all right, it seems to be as expected. And with that, pretty much all these data preparation and data pre-processing is kind of done. And now I'm going to just create my data generator to be passed into the model. So Shuffle. It's valid. And finally, my UNet model. First, I need to import segmentation models of Keras. Segmentation. It's one of the most popular package that you have, and I'm importing it as ASM. Framework. Not correct name, TF Keras. Oh yeah, of course, it is a TF.Keras. All right. Now my model is going to be UNet, and for the backbone, that is the actual network architecture that will be used for its encoder and decoder part, that is its upsampling, downsampling part. That I'm going to choose Inception ResNet v2. You can just look at it, these segmentation models documentation. Under the UNet, they provide quite a few options like efficient net B0 to B7, then all the ResNet, also mobile net, etc. And I'm choosing Inception ResNet v2, and then the other arguments. For the encoder weights, I am choosing ImageNet. Oh, sorry. ImageNet. I'm choosing Atom. Matrix, give it, we already have a defined function, dice coefficient. All right, I also want to give it loss equal to our BC E loss that we defined. BCE dice loss actually. Okay. What else? I think yep, I think that's okay. No. Define my checkpoint and early stopping conditions. Checkpoints. UNet model. Monitor. Monitor is a metric name. Typically, the matrices are set by the callback to save the Keras model. Okay, monitor will be val loss. Then verbose 1 save best only true. Equal to auto. Patience is 5. Mean delta 0001. Restore best weights. Okay. And finally, final model training. Create train generator. So what is our train generator? This is what we got from here after invoking the data generator method. Validation data is equal to val generator and now after the model training, now it's time to do evaluation on test data. For that, first I need to get my test dataset batches from the data generator and then apply model.predict to get the prediction. So first get my batches. Integer location. Model.predict. To that I have to pass the pred batches and verbose equal to 1. So this will generate my predictions, and then I need to, just like we did for the train data set, I need to plot the images side by side. That is original images, mask, and also the prediction. So for the train data set, we did it here. Let's go back. Oh, I think the output is in, okay, I'm talking about this. For the train data set, we only had image and mask, but for now I'm going to do for image mask and the predicted mask. So the code will be just similar to what I wrote here in this method called the plot mask with color patches. So in this long method, what we did, we created some color list, then took the mask from the channel, that is channel 0, 1, 2, representing mask stomach, large, I think it was a large intestine first, then small intestine, and then lastly the stomach. And then we created the mask with using np.maskedWhere and ultimately plotted it. So similarly, I'm going to do for my test prediction. Threshold, let's set it to 0.5. Again, using gridspec.gridsearch, gridspec.gridspec, and to that I have to pass in rows and in columns, in calls. That will be 3. So my colors and labels will remain the same, and that's actually will be just this. And now patches, that will be in patches.patch, then color will be equal to labels I as well, I in range len of labels. What I'm doing wrong here is I need to set the title. Set title, and similarly for AX1, it would be mask. All right, now I need another axis as well for the prediction, but before that, let's do the code for mask, and for which I can just copy paste from my earlier code here. This one I can just paste it here. So that's let me see what I mask. If I need to change anything here, np.maskwhere mask1 equal to false. So again, this np.maskwhere will put a mask where this condition is true. So in this line, anywhere in the array where mask1 is false, that will be completely masked, so I can only see the masked where with this entire line. So I think yeah, that all looks good, and only thing is I need to do the same for my third axis, which is for the prediction. Yep. And similarly, I need this code as well. So here, instead of mask 1, I need predict. Yep. Does it look bad in some way? Yeah, there will be an underscore. All right. And here as well, I need city. No, actually, I think I made a mistake here as well. There should not be any underscore. Let me delete all of them, because all I am checking is these lines. Okay, so these lines, that's why I was getting these predict 3 not defined, because I did not change the number here. This one is a third prediction of for the third mask. Yes, now it looks good. Actually, I still need to delete these underscore here. Yeah, now it looks good. I was doing some messing up with the naming. So I have, again, just to summarize here what these two blocks of code is doing. These 3 lines is just getting my 3 mask prediction values or prediction array values from the whole prediction. That's why I'm doing for these 3, I'm doing 0, 1, and 2 for the last dimension, which is representing the channel, and the channel in this dataset means the 3 mask representing the 3 channels. And then, because this is only the prediction, that is the probabilities, I need to apply the threshold and only take probabilities which are more than 0.5, because we defined the threshold here at 0.5. So I got my 3 prediction from the 3 mask, for the 3 mask, as predict 1, predict 2, and predict 3. And then here with np.mask_where, I'm just plotting the 3 predicted mask separately. That's all it's doing. Okay, now the final few lines of code. Set axis. Set axis off for AX in AX0, AX. Oh, I'm getting AX2 is not defined. Let me see. AX0, AX1. Yeah, this will be AX2. And this will be AX2 as well. And this is 1. Because I'm just first defining AX1 and then setting the set title. Okay. And then I started training, and I only ran for like, I think 10 epochs. And at the end of 10 epochs, my loss figure was actually showing promising numbers. So let's see. Here my dice coefficient was 0.85, IOU coefficient 0.83, validation loss of 0.23, and yeah, so that's kind of promising. But of course, I need to train it like for 50 or 60 epochs to get even much more better result. And now after the training, I also need to save the history data frame into my history.csv. Let's quickly do that. History. SP. And finally, I need to plot my progress in the training. So let's run that code. Plot. Whatever plt.figure. If I GURE, why it's not showing me, why it's giving me. Anyway, just go ahead, 20 by 20. Subplot. That's one row, 3 columns, and last one is in indices number. I need to take the range from history dot epoch -1 +1, and then history dot URY dot history. Here I need to give loss and label equal to loss. Range, actually just copy it down and then change for validation loss. This is validation loss, and here it will be val loss. plt.title loss. plt.x label is my epochs, and plt.y label is my losses. Legend. And then the next one, plt. Just copy it down and then I will see. Now let's change history.history -1 and +1 lost. It will be here dice coefficient, and train. Similarly here it will be validation that was validation dice COEFF, and label is validation, otherwise this will become dice loss. X label remains same, Y label is dice coefficient. All right, now again for the final one, which is IOU coefficient, let's keep changing it. Actually copy from here and paste it here. This will be 133. Train validation, label validation, IOU epoch lastly plp.show. And then I think I can copy a few things from this method that we wrote earlier. So my CMaps, that is all this listed color module, that will take a list of colors and create a color map. I can copy this from as it is. And yeah, then just start the loop of 8 rows. So I in range 8. And my mask will again be exactly similar what we did here. Let's just copy this. And now I need the predictions. So prediction underscore I will be Fred's, to that you pass I. So Fred's is the actual prediction from the model. Yep. And now prediction 1. So I'm just extracting data for the mask from the predicted tensor. Sorry, prediction I. From there, I take everything from the first 2 dimension and the last channel dimension 0. Similarly, I need to do for prediction 2, that is for the mask 2 prediction. And the last one is prediction 3. These are the prediction for the mask. And now because they are probabilities, I need to conditionally take everything which is more than the threshold, which is 0.5. So predict 1, PREDI setting. Predict 1 will be pred. What is my 1 second? And after running this cell, I got this output. Of course, it is only for 8 epochs, so our loss decrease is not so smooth. But we can see it's improving continuously over the epoch, and similarly for dice and IOU coefficient as well, they are improving. But again, it's only for 8 epochs, so a really good result can be seen probably after 30-40 epochs. I just want to name them like this: predict 1, predict 2. So my predict 1 will be predict 1 more than threshold, and then do an S type of np.float32. Similarly, do for predict 2 and also 2. Now the plotting related code, the x0 will be fake, and so yeah. specific dot. Sorry, that would be plot. One. And then colors. So colors. Norm 1 for I am in L1, L2 and L3. Finally, plt.legend and the matches. The box to anchor will be 1.1, 0.65. LOC is 2. Border AX ESPAD. Let it remain 0.4. So well, H color, face, what was the, I think that's face color. And finally, when I ran this particular cell, I got this image. So this is the original image at the left, then the mask of the original image, and then this is a predicted mask. And we can see the prediction are pretty good indeed, and we only ran like 10 epochs, and I can see that the predictions and the actual mask are almost identical. Red represents stomach, so here this is the stomach and this is large bowel, and we can see in the prediction as well pretty much the same positioning are showing, and that's kind of what we see in almost all the. Okay, this one is not so similar, probably. I mean, this is the case where the loss is high. Yeah, these two are also not so similar. Yeah, otherwise we are getting pretty good result. Yep. So this was the predictions, that is a model prediction applied on the validation dataset. Remember, we passed X valid, taking only these many rows to the data generator. But now the final step for this competition submission, that is we have to run this model and get the prediction on the test dataset. So let's do that now. Final prediction and generation of submission files on test data set. All right, the first step is I have to get the batches on my test DF dataset. Red batches equal to subset equal to test, shuffle equal to true, and no, sorry, it's false. Non-batches in, I have to divide the len of test df by batch size. Now start running the loop through the number of batches. For let's put it J, because I have put I in many other places. For J in range, for K in range 3, red image would be CV2 the resize threads Okay, now before proceeding further, quickly revisit the submission requirement for this competition in Kaggle. So I'm looking at the Kaggle's UW Medicine main competition page under the evaluation section, and for the submission they have a specific instruction here. So what they're saying, in order to reduce the submission file size, our metric uses run length encoding on the pixel values. Instead of submitting an exhaustive list of indices for your segmentation, you will submit pairs of values that contain a start position and a run length. For example, 1, 3 implies starting at pixel 1 and running a total of 3 pixels. Note that at the time of encoding, the mask should be binary, meaning the mask for all objects in an image are joined into a single large mask. A value of 0 should indicate pixels that are not masked, and a value of 1 will indicate pixels that are masked. The competition format requires a space delimited list of pairs. For example, 1, 3, 10, 5 implies pixels 1, 2, 3, 10, 11, 12, 13, 14, all separated by commas, but while submitting it will be space delimited. The metric checks that the pairs are sorted, positive, and the decoded pixel values are not duplicated. The pixels are numbered from top to bottom, then left to right. 1 is pixel 1, 1, 2 is pixel 2, 1, etc. The file should contain header and have the following format. All right. So while building the submission data frame, first here in this line, I want to resize probabilities to original shape. So I am using cv2.resize, and from my PREDS probabilities. And what is PREDS? PREDS is this. Here in this line, we got our PREDS by doing model.predict. And from this PREDS tensor, this is I'm going to get some particular aspects of the dimension. So the first dimension will be for J in range num batches. So this one will be J. Then from the second dimension I want everything, third dimension I want everything, and the last one I want K. And remember, K here I'm looping through the range of 3, so 0, 1, 2 are my K values, representing the 3 classes of mask. All right, and then I can access from test.df .loc. From there I into batch size indeed, and batch size plus J, and this is testdf.log, so I can pass the next argument to this, which is width. Am I doing it right? No, the width will come inside what I'm doing. That will come inside, and then test df again, and this time I into batch size plus height, plus I into batch size plus J height. Yes. Yeah, that looks okay, and I have to pass an interpolation Interpolation, I want to choose based on the nearest. Interpolation nearest, that would be cv2 dot inter internearest. Okay, and then just like previously, I need to take all the probabilities more than the threshold. Red image will be equal to more than 0.5 and convert that as type np dot, sorry, here I want to put d type equal to unsigned integer 8 uint 8 because this is a classification problem here. And finally my submission df mision dot lsc 3 multiplied by I times batch size. No, actually plus j indeed, yeah. And outside of this, for the mask in for the number this k representing one of these 0, 1, 2, and then prediction, that's a column value. And this will be equal to like we just saw in the Kaggle page, that we have to submit in RLE encoded format. And so this is where I'm going to invoke our RLE encode method that we wrote. To that I pass spread image. Here this should work just fine. And finally the very last cell, the last lines of codes will just be to convert these data frame into a CSV file, because that's what is required for Kaggle submission. Submission.to CSV. Okay. And index, set it to false here. Just print some sample, 20 of them. And finally, when I ran these, I got the submission data frame printed here as we see, and it conforms to the requirement of the Kaggle competition submission for this competition, that we have ID, class, and the corresponding prediction. And we can see that most of the cells here under prediction is empty because no mask were found, that is, no tumors were found in these cells. All right, so I think that's where now I just need to submit this file to the Kaggle competition from the output of this notebook. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with Pytorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.